Hi, everyone. Thank you for coming. Well, today I'm gonna present and try to read two papers to you. The first one right now here is SNRi target training for joint speech enhancement and recognition by Koizumi from and his colleagues or her colleagues from Google Research. The main issue this paper trying to address is the ASR under noisy conditions, which is a fairly difficult task. So this is why they propose these signal to noise ratio improvement target training. I think we can probably skip the introduction part because the most important takeaway message is that a typical single channel speech enhancement SE front end will cause some artifacts in speech. Usually you can hear this type of music like speech after the enhancement. And these things, although it improved the signal to noise ratio, but because those artifacts, it hurts the speech intelligibility, so the ASR accuracy in the following stage will suffer. Okay, and the usual way of handling this problem is to or by restricting the speech enhancement performance. So I don't want that good quality of the enhanced speech. I want to sacrifice some of the quality to a certain extent, so my intelligibility in this trade-off can retain to a certain extent, so my ASR accuracy gets higher. Okay, they talk about several algorithms which does this. Which they'll do this. And in their proposed work, they change the goal. Okay, instead of the speed enhancement, they want to produce a output signal with the target SNRi they want. Okay, this sounds like vague, but I will try to explain to you what their SNRi meant. Okay. Then they talk about the related works. First of all, the most, of course, if you want to do speech enhancement, probably lots of people were thinking about, okay, I want to have a microphone array. For example, the key, what's that? Amazon Echo has about several microphones on it, right? And also Google Home. I use Google Home. It's very good. I think Google Home probably has just two microphones, but it's fairly good. But what if you just have one single channel? Okay, that's also a real scenario. For instance, you call your friends at the subway station. Okay, it's very noisy, but there's no. Probably your cell phone has two channels, but the AT&T only gives you one channel. Okay, it's very noisy. So suppose you do multi-channel thing. They talk about the traditional way of doing this to introduce as fewer distortions to the process signal as possible. One reference pointer I can give you is MVDR technique. It's called minimum variance distortionless response. But nowadays everything is a neural network, so I think not a lot of people are using this. And also they talk about single channel speed enhancement. But this means the SE front end of the use in the traditional method or the method published before, they have to train both the speech enhancement and ASR losses. But your ASR backend uses the output from your SE frontend, right? Then that backend needs to be trained using only noisy speech, but also not only noisy speech, but also enhanced speech in various conditions. So this creates a mismatch between your SE and the ASR, correct? And in order to handle this, the proposed method, the work in this paper, they use a signal enhanced by different target SNRi as input to the ASR backend. Therefore, you can see that they avoid this overfitting issue which exists in the previous published works. Okay, and what exactly they do, how they achieve training the SE or ASR and ASR together by leveraging something they call SNRi. Okay, here's what they do. So far, any questions? Oh, we have another person coming in. Wenjie, how are you? Okay, I think Wenjie, you're first time here. Although this is a recorded session, but feel free to ask questions if you want, because I want an interactive communication, discussion. Okay, the method. The first talk about the traditional speech enhancement method, which is fairly simple to understand. Okay, first of all, the noisy signal X is composed by the clean one and the noisy part. Okay, this is the epic or classical additive model of the noisy speech. Well, I do not fully agree with this because I thought this is always done in a highly dimensional manifold, but it's an assumption, okay? And in equation 1, you can see that. Don't get confused by these people, the equations. It's very simple, okay? The final loss, SC-based loss, is a weighted sum of two losses, two SNR-based losses. Well, the first SNR-based losses is the clean signal versus the estimated clean speech. Okay, you can see S in here, Y1 is here. Let me scroll a little bit. Okay, and the second SNR-based loss is by calculating the ratio between the noise and the estimated noise. Okay, so you want to maximize the ratio of the first one and the ratio of the second one. It's a weighted one, so you do not end up with. So wait, why don't these people use the second term? Okay, what's the point of having this noise term here? I think the purpose is to emphasize the importance of not to overestimate the clean signal by allowing certain amount of noise to be left in the cleaned speech, so you don't end up with a very good quality speech signal but not very good intelligibility, which sucks for speech recognition. Okay, awesome. So I guess you guys with me. And here is what they proposed, SNR target training. Okay, it composes two parts. This first part, I think, is the main part. And the second part, you can regard it as a weighted part or the regularizer, or I think it's more like a weighted part. It's not a regularizer. Well, the first part, I think, you may ask, what is lambda? Lambda Lambda is suppose you have a speech signal with SNR of -5 dB, okay? Because in the training, these people or the authors, they use a simulated training data. What does that mean? They add the clean speech on top of the noisy, they add the noise on top of the clean speech, and they control the SNR. Okay, it's controllable. So in this way, they know what the clean speech is, and they know what the XNR is. Okay, and the lambda means the target SNR. So you ask, wait, is that the actual SNR? No, it's not. It's the lambda that can that is a suitable you can use in the speech enhancement. So the output of speech is the best or generate the lowest speech recognition error in the following ASR recognition stage. So it doesn't mean the actual SNR. Otherwise, it will just mention that SNR are real. Okay. So and then so you can see the target is that suppose a lambda is fixed. In this equation, lambda is fixed. And you can see the target is to make the target or output SNRi as close to this lambda as possible. So how do you calculate SNRi? So it's composed by two parts. The first part is very similar to this part, okay? It's the SNR regarding the clean speech and the estimated speech, okay? They want to get this part here is estimated speech related. And what the second part means is the actual SNR, you can see. A quick question, is this part fixed or not? I think it's fixed during the training because you can see that because they're using simulated training set. So this part is fixed and this part is fixed. It's a fixed term. You can regard this as a bias to the lambda. And the second part is called the source to artifact ratio. This is the part they want to minimize the artifact. And how do they define this loss, or how do they define the artifact? You can see it's very simple to understand. It's the SNR regarding the clean speech versus the artifact. Okay, and this is a weighted term of the clean speech. So you can see you want to minimize the SAR, and so you want to maximize the term in the log, okay, and then you want to minimize the E, which is the artifact. Okay, how do they define the artifact? Let's say the equation, I think it's equation number 7. So once you get the estimated clean speech, you get the difference of the actual clean speech. Then you try to have a orthogonal projection of this difference onto the subspace spanned by clean speech and noisy speech. Okay, then you get the main interpreter or E inter F. Okay, you get the main component, and the rest orthogonal component would be regarded as a artifact. I think this is a little bit new to me, but I think in the later on after this recording, I will try to read their paper, reference 32. I think it's worthwhile to read that paper. So this one explains why do they think the artifact can be or could be calculated in this way. Okay. And then now they try to train the ASR networks. So then you need to see the figure number 2. I think this figure is very clear to me. Well drawn, very good, very clear to me. First of all, you want to see how the SNR prediction net. This is the SNRi prediction net. So that's why it's not the actual SNR. It tried to predict the SNR and then fed this one into the SE front end. So this is why you can see in the equation, I don't know why I cannot zoom in, zoom out. So you can see it's right here in the equation 4. You want to have a lambda. Lambda here, you can see lambda here is the output of the prediction net being input into the SE front end. So SE front end take the lambda as a constant factor and try to optimize the what do you call that, SNRi value. Okay, you can see first, you can see this prediction net provides a what do you call it, the lambda for calculating SNRi, and the SE front end using the lambda. I'm sorry, I think I just read this paper today, so I might get confused about the lambda and the target I. Okay. Yeah, you can see the SNRi of the SE output Y. Okay. Oh yeah, I understand. So in this work, they have SNRi. So this input into the SE front end means the input SNRi or the target SNRi, and this one sent to SNRi and the following ASR backend stuff. SE front end generate a output SNRi, which is different than the target. So because you always have, so SNRi asks you to predict it, to generate this SNRi, but you always come up with something that's not exactly the SNRi value, okay? And the interesting thing is, once you get the ASR loss, you can see the error backpropagate. It can backpropagate all the way back to the SNRi prediction net. Okay, but the errors you got from the LSNRi when it runs the backpropagate in the green lines here, it doesn't. You don't use this gradient to update your SNRi prediction network because you can see a stop right here. Why? The authors clearly mentioned this because the predicted lambda is the prediction target of the SE front end. So if the SRE loss is backpropagated to the SNRi prediction network, this network would be optimized to output lambda, which is easy to predict by the SE front end. Very clear, very nicely written. This is their experimental settings. They use a simulated scenario, and they simulate lots of data. They simulate about 50K hours of data. I think there's something they need to improve is their testing set and validation set. They could use some real data set other than using the simulated data set, okay? Parameters, I think I will skip the parameters. Okay, let's see the table 1 first. This is their baseline. Once you get a bigger model, the WR actually got worse. By leveraging speech enhancement, you got much better WER, and by leveraging their proposal method, you get I think this is a significant amount of gain in terms of WER. What is interesting here is in figure 3, you can see once the input SNR is low, you can see they have the comparison between these two. But let's see the comparison between SER and SRI. Okay, you can see SNRi can generate the output SNRi more close to the target SNR compared to the SE in both cases, which is nice. So this means the network is doing the thing they're supposed to do, or better than the SE-based network. And also interesting thing is that once your input is noisy, for instance, minus 5 dB is very noisy, you can see your target SNR, and you can see the proposed method. Let's see the SNRi. Let's forget about the SE. Okay, it's pretend, or it's more likely to generate the exact or more close to target SNR. You see, the line is more like y equals to x. You see, the 8 is here, 8 is here. Okay, but once your input SNR is high, so it means the speech is more clean. Okay, more less noise in it. The proposed method, you can see it's more likely to generate a lower SNR compared to the demanded or target SNRi, which is interesting. They explain the reason. I think they need to have a better explanation of it. You can read this by yourself. That's their explanation, because they mentioned this is some under separation problems. But I think they need some more evidence to support their findings or their conclusion. Okay, Asr evaluation. I think there's not much to say. I've mentioned that in the table. The other thing is they did some in-depth analysis of why this thing works, or how this thing works. And they compare the source separation performance. Okay, so in table 2, these metrics, I'm not an expert on this, are the metrics for evaluating how good those the clean speech is separated from the noise after your speech enhancement front end. And you can see that under all the scenarios, I think, as they mentioned, that the proposal method works actually worse in terms of speech separation. But that's actually better, because if you separate the words, that means you sacrifice the quality for the intelligibility. Okay, I think this is very smart. It means that this is working as intended. I think this is also, I have mentioned that in the table already. And also, I think this is also interesting. I'm reading this, okay? These are gaps between the target and the output SNR in all examples. Therefore, it's necessary to improve the performance of the base front end itself. So this means the author thought that, okay, there's still much left to be done in terms of improving the speech enhancement front end. I think this gives us a very useful insight on the future development directions. Okay, any questions? All right, if there's no question, let's stop this recording.